One of the elementary properties of groups is what we call as the right cancellation law. This is how it is stated. Let G be a group under a certain binary operation star. If we have this equality, the operation or the result for B star A is equal to C star A, then we can just simply cancel this element on the right, that's why it's called right cancellation law, and just simply state that the first elements B and C respectively are equal to each other for all A, B, and C element of the same group G. So for this video, we're going to show that this is really true, considering that G is already a group under star. Together with this is the assumption that all the conditions such as associativity, existence of an inverse, and existence of identity element is already present or already possible for the set G under the operation star. So let's start with the proof here. Okay. So we are going to assume that B star A is equal to C star A. And these elements of G may take any form. It could be a real number, there could be functions if possible, and they could be matrices depending on what G is. What we just know here is G already a group under star. Now from here, what we need to do is to introduce a certain inverse so that we can just simply cancel A here and reach our intended result. The inverse we're talking about here, and since we're going to use the right cancellation law and we're going to cancel the element A on the right, we are going to introduce here its inverse, which is A inverse. And that is actually possible because G is already a group under star. This would mean the existence of the inverses for each element. This is actually possible. There are inverse of B, there's also inverse of C, but there is also inverse of A. But since we're just going to use the cancellation law here, or proving the cancellation law, we're going to introduce here the inverse of A, which is A inverse. And I would like you to introduce that on the right because we have here the right cancellation law. Hence, we're going to treat this as 1, and we're going to operate it to the inverse of A. Okay? So we're introducing here, we're operating this with the inverse of A. Now, doing the same thing on the other side, C star A, we're also going to introduce the same so that we retain the equality presented already earlier. Okay? So we are introducing here the same inverse. Now from here, we are going to use the next condition, another condition for a group we call associativity. Because we have here groupings and we would like to create another association or grouping where we simply group A and A inverse together with this here side as well. And this is possible because G, or one of the conditions of G to be a group under star, is associativity. Hence, we have this form. B star A inverse. We associate this to that, doing the same thing on the other side. C star, we have here the grouping of A and A inverse. Okay, from here, we have these expressions or expression present on both sides of our equation. And if we are going to operate whatever would be this binary operation, A and its inverse, this is equal to the identity element of the group, and it's only one. It's unique for each of the group or each group. So for group G here, E is actually the identity element of this group. And this is also possible because one of the conditions for G to be a group under operation star is that there exists identity element for all the elements on our set G. That would mean we have here B star E. Looking into the other side, you have C star this as well, E. Now, we only have one more step, and this on simply the simplified form of this. We call this identity element because whatever you operate, or whatever element you operate with that, it's the element itself. So B star E is just simply B. The other side, C star E, is simply C. And this is actually our intended point on our theorem or proof for the right cancellation law here, which states that if you have this expression, you can simply cancel the common element on the right, leaving with these elements as the equality here. So from here, we reach to that, and that's the proof for this right cancellation law. This again, properties, laws, and theorems. Please subscribe now.